So I'll go ahead and get us started. So yeah, welcome and thank you to everyone for attending this seminar. Today's presenter is Nicholas Loveday from the Bureau of Meteorology in Melbourne, Australia. He spent 5 weeks with us back in August and September at the DTC, working on his DTC visitor project, and he's since been finishing up his results and his visit this past October back in Australia. So a brief background on Nick: he obtained his BS in atmospheric science from Monash University in Melbourne in 2014 and completed a graduate diploma in meteorology at the BOM in 2015. And then from 2015 to 2020, Nick held positions at the BOM as a meteorologist and later a senior meteorologist, specializing in the operational tropical weather forecasting, specifically with respect to severe thunderstorms, tropical cyclones, aviation, marine, fire weather, and public weather forecasting. And his current role at the BOM is as a verification research scientist, and he serves as a scientist lead on several projects, including a project for evidence-targeted automation, or ETA, working on evaluations of operational meteorologists' forecasts against automated systems to improve forecast accuracy. And then his other projects focus on evaluation and development of heatwave forecast and warning systems, as well as severe weather and severe thunderstorm warnings. From an engineering perspective, he's a developer for the BOM's operational verification system, Jive, as well as the open source SCORES verification package. And that SCORES verification package contains a number of similar metrics that are found in MET+, but also other metrics such as threshold-weighted scores. And some of that he'll be discussing in his presentation today. So his work in the DTC has been related to using those threshold-weighted spatial verification scores to compare a data-driven model to a physical NWP model. And with that, thank you for presenting, and I'll let you take it from there.
Okay, great. Thanks for that introduction. Yeah, so as you mentioned, I'm going to be looking at combining threshold-weighted techniques with spatial verification methods to compare one of the data-driven pure AI models against a physical NWP model. So I want to start by just providing some simple hypothetical use cases of NWP models and these data-driven models that are being developed. So in this first example, we can see Mike here has decided to go back into operational forecasting, and he's in charge of the severe thunderstorm forecast for the afternoon. So, sorry, I can just hear someone laughing there.
That's me.
So, yeah, Mike wants to use the high resolution NWP model to look at what kind of mode of convection he expects will occur during the afternoon. Now, another use case, Louisa is in charge of tropical cyclone forecasting. And she's taking the models and basically taking like the wind and pressure fields and getting some track forecasts and intensity forecasts for an ensemble. So that's a very different way of using the models. Now, John, he just cares about what the temperature forecast will be at his location tomorrow. So he's just interested in the forecast for a single point. And he doesn't care about what's going on in other locations. So he doesn't care about any physical consistency. He just wants the best forecast for his location. And so this is kind of what people who use weather apps often want. And often these are post-processed models that are fed into these weather apps. But, you know, in the future, potentially they could just be, a pure data-driven model feeding into this app. And then finally, Tracy is planning a holiday to New York, and she looks at the forecast for the next day, and she kind of looks at a square and a neighborhood around the area that she's going to visit. And she wants to think about, like, what's the likelihood of flooding on my trip to New York? So in this case, the heaviest rain is offset from the city that she's going to visit. But she can use that information in like a probabilistic sense to get a sense of the likelihood of that extreme rainfall occurring. So my point is that NWP models and these new data-driven models that are being developed are used in a variety of ways. And that means, as part of our testing and evaluation frameworks, we need to construct verification approaches that align with these various frameworks and take a multi-pronged approach to our verification of NWP and these data-driven models. So the approach that I want to look at is similar to the use case of the heavy rainfall around New York, in that I want to evaluate how good the models are at predicting extremes when you just take a neighborhood around your location and use that to generate a probabilistic forecast around that point for you to make decisions. So as part of this approach, can we set up this approach so that it can be weighted towards extremes, such as heavy rainfall, or can it be weighted to a range of key decision thresholds, such as aircraft icing, which tends to occur between -20 and -10 degrees Celsius. And we also want to take into account as much information as possible. So we don't want to just look at, a single binary threshold. We want to look at a whole range of decision thresholds. So we want to make sure that we're not only, correctly forecasting whether it's extreme or not, we're correctly forecasting how extreme it is. And as part of this approach, can we create an approach that doesn't reward biased or hedged forecasts, and it avoids selection bias by conditioning on observed events? So there's a quote from Sebastian Lurch down below where he says, "In a nutshell, if a forecast evaluation proceeds conditionally on a catastrophic event having been observed, always predicting calamity becomes a worthwhile strategy." And so I've seen this done a little bit when it comes to evaluation of extremes with these data-driven models, where people just condition the verification on extreme observations. But that's really going to reward forecasts that may have an over-forecast bias. So in this particular framework that I'm looking at, I want the models to be reasonably well calibrated. And so there's been some good techniques that have been developed over the recent decade to be able to handle that situation of evaluation of extremes, but they're all point-to-point based verification methods that suffer from the double penalty issue. So in our approach, we want to be able to reduce that impact of our double penalty issue within like the area or the neighborhood that we're looking at. So the double penalty issue is when your forecasts might look realistic to the observations, but it's offset slightly. So you get penalized for forecasting where the event didn't occur, and you get penalized for not forecasting where the event occurs. So you end up with this double penalty. So we want to account for that. And as part of our approach, we ideally want it to work with point observations. So some countries like the US have these really great gridded rainfall analyses, but not every country does. So many countries have poor radar coverage, or if they do have a gridded rainfall analysis, it may not be appropriate for verification. So for example, in Australia, in this use case, I want to look at 6-hour rainfall, but we only have one gridded rainfall analysis, and it's for a 24-hour period. And it's aligned with 9 a.m. local time. And we have 5 time zones in summer. So that means that not only will the rainfall observations not be aligned with the model validity periods, those rainfall observations are spliced up depending on what state you're in and kind of joined together. So it's not even one coherent period. And as part of this approach, can we compare models with different grid resolutions without having to do any regridding to that lowest resolution, as that may unfairly penalize a high resolution model that contains this rich detail in the higher resolution grid. And if we're looking at extremes, can we set up our approach so that we can normalize our verification scores based on climatology or climatological extremes? Otherwise, our results might be just heavily weighted towards the locations that are more climatologically, have these extreme events more climatologically frequently. So the approach that I'm taking here is I want to take two existing techniques and combine them together. So the first technique is threshold weighted CRPS, which I'll go into more detail. And the second approach is HRRR, which I'll talk about. And we're going to use this to answer the question around how good are the forecasts around an observation or a point when they're used in a probabilistic sense across different spatial scales. So to introduce HRRR to you, so this was developed by Marion Mittenmeier, and the approach is you have your point observation and then you construct a neighborhood forecast around that observation point. And you might do this across with various neighborhood sizes. And when you have your neighborhood neighborhood forecast, you can then use that to generate a pseudo ensemble, which gives you basically you can derive a predictive distribution from it. So it gives you a sense of the range of possible outcomes that could occur at that observation point. And then from that, you've got a pseudo ensemble and you've got an observation. You can go ahead and calculate your verification score, such as the CRPS. Now, what can using CRPS with HRRR tell you? Well, it can basically tell you how useful your model is with some very basic spatial post-processing. And it can be used as kind of like a proxy of someone using that forecast in that neighborhood sense around their location to make a decision. So on the left-hand side is an example. Let's just say this is rainfall, and the grid cells with orange and red indicate the higher intensity forecast. And in the middle, that circle is our observation, which is a relatively high rainfall amount. But if you look at that forecast against the observation, you might say, well, captured the intensity, but it was just offset slightly. So it was a pretty good forecast. And you wouldn't want that to be penalized unfairly if you were just looking at that single grid point. On the right-hand side is, what a lower resolution fuzzier model, like one of these new data-driven models might look like, where it just kind of it produces a forecast and smears the rainfall everywhere, but it doesn't really capture the intensity there. And if you're just to verify them against that single grid cell that they're on, that lower resolution model on the right-hand side might score better. But if you take this neighborhood approach with HRRR, then your higher resolution model that captured that intensity on the left may score better. So your expected CRPS for a given point will be optimized by predicting the neighborhood that can be used to produce the best predictive distribution for making decisions. Okay, so now on to CRPS. I don't want you to worry too much about the details of the equations. I just want you to note that The CRPS for ensembles can be decomposed into two terms. So the left-hand term is just the mean absolute error for all ensemble members, and the right-hand term is a spread term. And this is the fair implementation of the CRPS for ensembles. Now, to go to the next step of creating a threshold-weighted CRPS, you take the equation above and you just need to introduce what we're going to call this chaining function V that goes into 4 different places in the equation. And I'll show you how we construct that chaining function V. So let's say we come up with a framework for how we want to weight the verification results as a function of decision threshold. So that top plot there shows our weighting function, where you have a weight of 0 for decision thresholds less than 23 millimeters, and then a weight of just 1 for thresholds above that. Now, to construct our chaining function, we take an integral of that weight function and produce our chaining function that we can put into our threshold-weighted CRPS equation. Now, to give you a graphical illustration of what's going on, where we want to weight kind of like the tails of decision thresholds above our threshold T. On the left-hand side is a graphical illustration of how CRPS works. So our forecast is the blue CDF, so we've got a predictive distribution, and the observation, since we only get one value realized, is we have this sharp-looking CDF. And the CRPS is that area in between those two curves if you square that area. Now, on the right-hand side, we can see how the threshold-weighted CRPS works if we're just looking at kind of those upper tails above threshold T. And the threshold CRPS aligns with that area between those two curves above that dashed line squared. And so that was just an illustration of weighting an upper tail. So these are some examples of different weights. So that previous example kind of aligns with like the idea of the upper tail on the top right plot here. If we were to just have a constant weight of 1 for all decision thresholds, so the top left-hand one there, we just recover the standard CRPS. Down the bottom left, that shows what our weighting function could look like if we are interested in an interval, such as a range of temperatures for aircraft icing. And then the bottom right just shows you could just build your own custom weighting function. So as part of this project, I developed 3 threshold-weighted CRPS functions which is an open source Python X-ray-based code, and we've built this into our scores package, which you can go off and use. So I've constructed 2 kind of simple functions. So one that works where you specify the tail that you want to look at. Another one where you want to specify the interval, the range of the interval to look at. And then I made a third one for more advanced users who want to go ahead and construct their own chaining function to do their own custom weighting. As part of this, implemented with both the fair and empirical implementations, set it up with a decomposition, which I'll explore later on. And it's been built properly with complete unit test coverage and documentation. As part of this, I also put together a tutorial that people can work through for using threshold-weighted CRPS with this code on real data. So this is just looking at threshold-weighted CRPS in a non-HIRA framework. So like if you have an actual ensemble forecast, gridded ensemble against a gridded observation, and you can run this tutorial in an interactive notebook or view it just in a web browser. Now the tutorial works through how to generate those chaining rules and how those chaining rules work. It then allows you to pull down data from the cloud for the ECMWF IFS ensemble, neural GCM, which is kind of a hybrid physical data-driven model, and the ERA 5 data for observations. And that data just comes down in a nice format in X-ray that you can pass into scores, and we can use this to evaluate extremes, intervals, and custom thresholds with the threshold-rated CRPS. Okay, so now onto the use case of this method in my project. So the two models that I want to compare is I'm going to compare the GraphCast model. Now, this GraphCast version was initialized with the GFS conditions because that was the particular version that I could get access to that had data for the longest period of time. And I wanted a lot of data if we were going to look at extremes. And then the HRRR model was just one of the most well-used physical models, and it's a high-resolution model. So you can see that their grid resolutions are quite different to each other, and I think that is a nice use case for demonstrating, evaluating these models with different grid resolutions. I just took the OOZ base run. I'm looking at 6-hour accumulated rainfall or precipitation, and I'm looking at over 2.5 years worth of data. And so the lead times I've just lined up with the HRRR, so we're looking at lead times 6 to 48 hours. And I've matched all the data between the models, so it's a fair comparison to account for any missing data. So I've gone and constructed some various neighborhood sizes that are equivalent between the two models. So the first neighborhood size is just a 3 by 3 kilometer, which is just a single grid point with the HRRR, and the GraphCast doesn't go that fine. The next one is 27 by 27 kilometers, where you basically have a 9 by 9 grid with the HRRR, and that's the equivalent of a 1 by 1 grid with GraphCast. Then I have a much larger neighborhood size, which is 111 by 111 kilometers. And with the HRRR, that corresponds to 27 by 27 grid cells, and GraphCast is 3 by 3 grid cells. So why was I interested in GraphCast compared to HRRR? Well, as I mentioned before, they have very different grid resolutions. So we want to be able to use this approach to understand and quantify any gains from having that higher resolution model. And I think with these new data-driven AI models being developed, there's a lot of interest in verification around extremes. So this can be a really nice approach to do it in a quantitative sense that can be really useful for complementing the case study approach. And one other thing about these new data-driven models is that they often produce these fuzzier predictions, which may be optimal for, say, mean squared error at a given point. And we can use this approach to explore the impact of a point-based threshold-weighted score. So when we're just evaluating at the point against taking a spatial threshold-weighted scoring approach. So the observation data that I used, I took almost 800 stations across the US. I looked at 6-hour accumulated precipitation, which was derived from the 1-minute ASOS data. I implemented some basic quality control, and I also did some station density weighting with the verification scores using ECMWF's method. And that basically just ensures that, you know, the results aren't weighted to those areas of the country where you have a higher density of weather stations. So now onto some results. So to begin with, I'm just looking at CRPS within the HRRR framework, and I've just shown you the results for the HRRR models across the 3 different neighborhoods. So the results are plotted across lead time in 6-hour intervals, and with CRPS, lower values are better. And what you can see is as you increase that neighborhood size and start accounting for things like the double penalty issue, you can see that your scores do start improving, which is what we would expect. Now, when we add GraphCast to the mix, we can see that the performance of GraphCast for just the grid point and also the neighborhood is somewhat similar to just the HRRR when evaluated at the grid point. So now onto our threshold weighting. So we could do our threshold weighting where we just pick a hard fixed threshold of a rainfall amount everywhere. And I did this initially and just picked a threshold of 50 millimeters for a 6-hour rainfall period. But when you do that, you can your results may be dominated by areas where the heavy rainfall is climatologically frequent. So as a way of kind of like normalizing the extremeness, I wanted to set this up so the threshold varies spatially using 6-hour precipitation climatologies. And I derived these from 30 years of ERA 5 data. Now, these climatologies of ERA 5 will differ a bit from what will be observed at the rain gauge level, but we don't have that ASOS data going back in time for all those stations for that period of time. So we can use the ERA 5 data just as a proxy of what constitutes a heavy rainfall event. So I've repeated this for 2 thresholds, the 99th percentile and the 99.9th percentile. And I'm doing just like an upper tail weighting with my threshold weighted CRPS. So if we jump to the results here, the solid lines, which are the HRRR, we can see this makes an even bigger difference. Like the neighborhooding makes an even bigger difference when we're looking at these heavy rainfall events and performance around heavy rainfall. What we can see though with the GraphCast is that the neighborhooding approach doesn't change things all that much. And that's potentially because the GraphCast is a smoother model, so you're perhaps less likely to capture the extremes properly, even if you do construct a neighborhood around a point. And we can calculate the differences between these 2 models. So here I've just taken the difference between GraphCast and the HRRR for equivalent neighborhood sizes. And you can see that in the short term, the HRRR performs better, whereas as you drift out towards the longer term, the HRRR loses skill relative to GraphCast. And these confidence intervals were calculated using the Herring-Gentzen modification of the Diebold-Mariano test statistic. We can then repeat the experiment for the 99.9th climatological percentile threshold, and the results are really quite similar again. And we can construct differences again, and it tells us a similar story, that the HRRR is better in the short term, but GraphCast better in the long term. So I've done 2 different decompositions here to try and gain some further insights as to what's going on. So this first decomposition, which I haven't seen done anywhere before for CRPS or threshold weighted CRPS, is to basically decompose that first term on the left into over forecast penalties and under forecast penalties. And this can give us an idea of if, the penalties with our threshold weighted CRPS, if they're coming from the model just over forecasting heavy rainfall or if they're under forecasting heavy rainfall. So back to just the 99th climatological percentile threshold. So the HRRR, and I'm comparing the HRRR against the GraphCast on equivalent neighborhood sizes. So we've just got our threshold weighted CRPS plot here. And the next thing that I want to do is calculate the under forecast penalties. So the penalties that the models get for under forecasting heavy events. And what you can see here is that the GraphCast gets a higher under forecast penalty than the HRRR. So the HRRR is under forecasting extremes less than GraphCast. Then if we look at the over forecast penalty with the fine dotted lines, we can see with the HRRR, the blue lines, the under forecast penalties are similar-ish to the over forecast penalties. But when we look at a GraphCast with the over forecast penalties, they're getting close to zero. And you can see that GraphCast is getting penalized for under forecasting so much more than it's getting penalized for over forecasting. And then there's the spread term, which accounts for the size of your predictive distribution, and the spread term, because the HRRR has more ensemble members, that offset with the spread term is much lower. And that offsets those over and under forecast penalties that we were getting with the HRRR, which brings the threshold weighted CRPS down. So that total threshold weighted CRPS is the sum of those three penalties that I've shown there. And so that kind of raises the question of, well, if GraphCast is not if it just keeps on, if it's getting heavily penalized for under forecasting extremes, but it's not really getting penalized at all for ever over forecasting extremes, might be really interesting to look at the base rates. So here I've just calculated the ratio of the count of forecast values above a threshold compared to the count of the observed values above a threshold, and this is done across all lead times. And so I've just done this for the point-based HRRR and the GraphCast HRRR. And a value of 1 implies that your forecasts and observations have a similar base rate. Values less than 1 indicate that your model is predicting the extremes less frequently than they observe, and values above 1 indicate that your model is predicting more extreme events more frequently than they occur. So I've done it for a few different thresholds. So that 99th percentile threshold, well, actually for all thresholds really, the HRRR, that value is close to 1, which I think is a good sign. But yeah, so from the left with the 99th percentile, GraphCast is only predicting extreme values or heavy rainfalls roughly 54% at the frequency of 54% of the time that they're observed. When we go up to the next extreme threshold, the 99.9th percentile threshold, we can see that it's only forecasting those heavy rainfall events above that threshold, roughly at a rate of 10% of what's the frequency that they're observed. And then I also did it just for a fixed 50 millimeter threshold because some of the more climatologically dry areas in the US, those rainfall thresholds with the 99.9th percentile might be down closer to, say, 20 millimeters in a 6-hour period. So I've just done it as a fixed 50 millimeter threshold everywhere. And when we do that, GraphCast is only predicting those rainfall above 50 millimeters at a frequency of roughly 2% of what is observed in reality. Okay, So now on to the second decomposition of the threshold weighted of CRPS. So the mean CRPS can also be written as the integral of the mean Brier score across all decision thresholds. So that allows us to decompose the CRPS based on the Brier score. So these results here are for the 6-hour lead time. So on the left-hand side, you can see that for the lower rainfall amounts, yeah, it's pretty clear that the HRRR is doing better than the GraphCast. And then those results start to converge as you get to more extreme thresholds. One thing that's worth noting is that when we take into account the neighborhooding approach, that crossing point between the solid and the dashed lines, when we look at the blue HRRR just point-based, it crosses with that GraphCast line early on. Whereas later on, like if we look at the right-hand side where we've got just a log y-axis to highlight the differences a bit more, you can see that green line just travels just below GraphCast pretty much right the way up. It's also worth noting that, you know, if you just do a single Brier score calculation using like the neighborhood approach on a single threshold, you might infer that there's not much difference between them at all. Whereas when we use the threshold weighted CRPS and we're looking at the information across that range of thresholds, it gives us much more information to infer the differences in the models, and if gives us enough information that we were able to say if one model was statistically significantly better than another. And I've repeated this again just for the 30-hour lead time. So this was one of the lead times where for threshold weighted CRPS, GraphCast did better for the extremes here. And you can even see here at the lead times, on the left-hand plot here, for smaller decision thresholds, you can see that the HRRR model starts crossing the dashed lines of the GraphCast curve earlier on. So looking towards the future in terms of where could this work go, well, I think there's the possibility of exploring HRRR in a multivariate framework. So this could be used to look at compound events, and you could use a multivariate scoring function such as the energy score. And you can look at, compound events, say like rainfall across multiple time steps to introduce that time temporal component into it. You could also do multivariate verification with things like fire weather verification, which depends on, say, wind, temperature, and dew point. In this particular framework that I set up, I wanted the scores, the models to be well calibrated, and if they're not, they should be penalized. But potentially there might be other frameworks where, you know, you're okay with having a bias forecast if it provides good discrimination abilities. So perhaps we could think about ways of decomposing scores in the HRRR framework in a way that we could have a discrimination component to look at. The other thing to note is that with CRPS for ensembles, with that spread term, the term on the right-hand side of the CRPS and threshold weighted CRPS, that spread term becomes computationally expensive when you have really large numbers of ensembles. So with the HRRR 27 by 27, you know, that's getting up around 800 ensemble members, and that's doable. But if you were to start increasing those neighborhood sizes and get much better, or you had like an even higher resolution model, then you're going to start running into computational challenges with calculating the CRPS. So I think there's room to explore ways that those calculations could be improved. It would also be really interesting to add a climatological reference forecast to the verification, which is basically a reference forecast that never forecasts extremes. And we could use that as a proxy of, are we actually getting much skill when it comes to extremes? And I suspect that the GraphCast scores would have been quite similar to a climatological reference because it doesn't forecast extremes as much. And what would be interesting to do would be compare this framework to other spatial methods. And I know REL in the past has done a lot of work in these spatial forecast verification intercomparison projects, but maybe it's worth considering if there could be a phase 3 of this and with a focus on extremes. So I'll just throw that idea out there. So to summarize these results and what I've shown you, we've demonstrated a way that we can construct a framework of using threshold-weighted spatial scoring rules, and we can use them to evaluate how well forecasts predicted extremes for a user who wants to kind of look at the forecast over an area and a neighborhood and use that to help them make decisions. The results showed that the performance of the HRRR was more strongly impacted by the neighborhood size compared to GraphCast, and this was particularly the case when we're looking at extremes. And across all thresholds with just the CRPS, the HRRR was ranked as performing better on equivalent neighborhood sizes compared to GraphCast. And that was particularly the case where we're looking at the lower rainfall thresholds, which kind of dominate the total CRPS score. But when we went to look at the extremes, the HRRR performed better on equivalent neighborhood sizes than GraphCast at short lead times. But when we went to longer lead times, GraphCast was performing better. So GraphCast, when we started decomposing the scores, we saw that GraphCast rarely over-forecast heavy rainfall event. And when we looked at the base rates, it wasn't predicting the extremes anywhere near as much as the observed frequency. Whereas the HRRR model was penalized roughly equally for over and under forecasting heavy rainfall, which I think is a good thing. And so as part of this project, I made open source Python code in our scores package that people can use if they want to go away and calculate threshold weighted CRPS. And there's a few different functions there that you can use, and a tutorial notebook that will show you how you can run that through data that's been put into an X-ray format. So looking forward to future collaboration opportunities between the Bureau and DTC. So I've mentioned that I've built these new scores into our Python, open source Python package. And I think there's the opportunity for collaboration there in getting new verification scores into MET and MET+. So the way this could work would be the new metric could be developed or implemented in scores, which is in Python code by scientists, because it's just too difficult for most scientists to kind of approach MET and then do that C++ implementation. So the scientists can develop the new metrics in Python. That code can either be given to the DTC developers to convert across into C++ and implement in MET, or MET could potentially be updated to call scores using a Python to C++ interface. And then those scores would then flow on to users of MET+, and that would really help support the international use of new verification methods in operations and help the research to operations pipeline. So our focus at the Bureau is on 2 verification tools that we think complement each other really nicely. So the first is MET+, and the second is our Jive verification system, where we're replacing the core of the verification calculations with our scores open source package. And there's a couple of papers on those 2 verification tools that have recently come out this year. And so on that second idea of this Python to C++ interface, John HG has created a GitHub issue on MET to consider a new MET tool to interface with the scores Python verification package. So you can imagine this like, you use all your great pre-processing tools in MetPlus. And then if you wanted to call, say, a scores, or it could even just be like a Python-based interface Met tool, that does your verification calculation, and then you get your output, and then you can use the MetPlus tools to visualize your output. And at the moment, a lot of most of the Python in MetPlus is kind of upstream of the verification calculation, but going down this path could really open up MetPlus for Python embedding in the actual metric calculation component of Met itself. And this would also make it easier for the community to add and contribute new metrics into Met using Python, given it's the C++ side of things is just too difficult for outsiders to come in and build these new metrics into Met. And this approach would give MetPlus access to a range of metrics that it currently doesn't contain, such as a whole lot of these new metrics that have been developed over the last decades for evaluating extremes. So with that, I'd like to say thank you, and thanks to everyone who helped with my visit. I had a really wonderful time in Boulder, and it was great getting to know you all. And yeah, I'd definitely love to come visit again one day in the future. So thank you.
All right, thank you, Nick. And we've got about 10 minutes for questions. And I see Molly's hand up.
No, I was trying to clap and I clicked the hand raise button. Sorry.
I thought it was weird that it went away. I was like, well, maybe
I see the hand button and I click it and it doesn't do what I think. I'm sorry. But excellent talk, Nick.
Thanks, Molly.
Matt, you have your hand raised.
Hey, Nick, appreciated the talk. It was good. I do have a question, though, about the approach when you're working with some very rare things and especially very spatially isolated type of events. So let's think aircraft turbulence, where a moderate turbulence, as you expand the neighborhood, from a forecast sense, you don't really want that whole neighborhood filled with, say, moderate turbulence. But that's going to optimize your CRPS score, right? If you have every grid, every pixel in there forecasting the correct magnitude, you'll have a nice step function aligning with your observation. But it's physically not correct. Does this question make sense to you?
Yeah, sure. So yeah, that would be on, I guess, just like a single case. But if you kind of repeated that over time, it should even out that it's going to be optimized by over time, your expected score over time will be optimized by producing kind of a realistic neighborhood. So okay, so take that example. Okay, so let's just say you forecast moderate everywhere, but observed it's kind of just in one location, right? Okay, right. But let's just say over 100 use cases, that observation changes around in different locations. So you might get a really great score in that particular case where you've got moderate at that point, and you forecast moderate everywhere. But then all those other cases where at that point you don't observe moderate, but you forecast moderate everywhere, you're going to be penalized very heavily for that.
I see what you're saying. I guess I still think that there are, so one thing's with the RRFS and the convection, it produced overly large convective cores. Yep. Let's pretend that it was really good with the location, though, of those cores. So that would be a case where you'd have excessive coverage, but the right location. And so you would, I think, minimize that penalty that you were just talking about in the broader sense, right?
Yeah, and I guess the other thing to think about is, if you have the more weather observation points that you get, they're going to give you information because you're constructing neighborhoods around all of those. So if you have, you know, other observation sites, and like, so if the forecast you're saying like just blows up convection over a wide area, but then it's only observed in one point, you know, you might get a good score for that one point, but those other points around it where you don't observe that heavy convection, you're going to get penalized there.
Yes, I agree
So
with
yes.
that. I guess brings up the question when you're applying this, say either to a grid or to a dense set of obs, is it appropriate to slide it where you've got a lot of duplicate information nearby, right? So you have a lot of correlation between your 27 by 27 here and your 27 by 27 shifted one? Or should you step it so that you're avoiding that overlap?
Yeah, I think that's a good question in terms of thinking about this idea of spatial dependency in the calculation. So I guess like going back to how I started the presentation, where I was talking about there's various different use cases for NWP, you use it in different frameworks. I just wanted to be kind of like precise with, you know, we're using one framework to basically like, this is how we're going to work. We're like that New York example, we're going to construct this neighborhood around this point, and we're going to use that to produce our probabilistic forecasts that we're going to evaluate. So I just want to make clear that this like method isn't going to cover each case, but I think it's kind of like a useful tool to be part of like the testing and evaluation framework in assessing the model when used in that particular decision-making framework, which could be a proxy of, you know, how many people might interpret a model.
Yeah, that makes sense. I agree. By the way, it got dark through the course of your seminar and I didn't get up and turn on a light. I'm not attending from a cave or something, so just.
Sure, I didn't even notice. Thanks.
Nick, great talk. Thank you. You mentioned early on, kind of in passing, the ECMWF has an algorithm they use for assigning weights based on point observation density. And we have an issue in MET to add similar functionality. One is using Voronoi tessellations based on requests from NOAA EMC. I'm wondering if the ECMWF method is widely used, is standard, should also be supported in MET, assuming that it differs from the Voronoi tessellations. Yeah,
sure. Yeah, I'm not an expert on the different station density methods, but I know it's at least widely used in Europe, and I know Canada's also looked at it as well. So that's the one that's based on written up in the SEEPS paper, the Mark Rodwell one. But yeah, potentially it's worth considering, but I wouldn't say that I'm an expert in the various different kinds of spatial density weighting for stations.
Okay, great, thank you.
Any other questions? And Nick has provided his email there on the screen. So if you have further questions or want to chat about this work some more offline, you can message him about that as well. All right, well, thank you, Nick. I thoroughly enjoyed that presentation. Very well done. And hopefully we can get to work with you in the future, maybe another DTC visitor project or something, and especially maybe even getting some of these metrics into usable in MET. So look forward to it. And with that, I will give everybody about 4 minutes back to their evening or day, I guess, since you're just starting your day, right? And thank you everyone for coming.